Okay, before the coffee break, we came down to that this is the problem, and to be more specific, if we look at this, then actually this notation, the delta Q n plus 1 is minimal, means actually that you have delta Q1 squared plus delta Q2 squared plus etc. until as many as there are delta Q's. And then the sum of that is minimal for the delta Q's. Then you would say, well, that's an obvious answer. Then the delta Q should be 0. Yeah, the delta Q should be 0, and plus that the delta Q should fulfill the constraints. And that is why we say, well, we need to add these constraints by means of Lagrangian multipliers. And if you do that, then you get the following form of equations. The first is just the identity, and here we have our delta Q's. And I now drop n plus 1 because it was step n plus 1. And you would say, well, the result should be that these delta Q's are 0, right? That is the real minimal solution. But we have the constraints, and according to this Langström's method, we have to take into account these multipliers, and I on purpose took no lambda but a mu here. So the C is in this case the tangent, so C, let me say C, the matrix C is the dCi dQj, so that's the Jacobian matrix. So that should be 0. Constraint minimization problem, and then of course on top of that we have this linearized equation. Where is it? Here, this one. So we have C times delta Q, and here's the 0, is minus, and then what do I write? The C of the Q with a slur. The approximate position, the errors we make. This system looks very familiar to us, of course. It looks a lot like the DAE we usually derive. But then here we have a mass matrix, and here again the Jacobians, and then here forces, and here second order terms. Anyway, what is the solution of this system? Well, let's do an example where we do a little bit of a shorthand notation, otherwise I have to write so much. So the delta Qn I'm gonna write just as delta, and it's a vector, of course. The mu I keep, and then the minus C of Q tilde I just call minus the error E. Yeah, and then the C I keep the C. So then the equations become a bit shorter to write. So I get identity C transpose matrix C zeros. Then I get my deltas here, my increments. I have my Lagrangian multipliers here, and then I have 0, and I have my error in the constraints. Okay, and the solution we now need, we need to solve for our delta, and we get for free, we get our mu. That's what we get for free. We don't want to solve for that, but it's some extra. Now, how are we going to solve that? In this case, it's super simple, actually. You just can do it by hand, symbolically. Because from the first equation, so the first equation, what does it read? It reads delta plus C transpose times mu is 0. So my conclusion is, oh, my deltas are equal to minus C transpose times mu, right? Very simple solution. I don't know what mu is, but we will get to that in a second. Now, how do we find mu? Well, I take this and I put that in the second equation. So I have C times this delta equals minus E. Or in other words, when I substitute that here, what do I get? I get minus C times C transpose times mu equals minus E. Yeah? Or in other words, I get C times C transpose times these mu is E. And from that I can solve, hopefully, what my multipliers are. Now, am I able to solve that? Well, this matrix, what will the size be? Will it be a very big one or a very small one? So in the case of our closed loop system, let's say, what are the dimensions if we think of our closed loop system? So in our closed loop system, how many coordinates did we have? 3 coordinates, alpha, beta, gamma, right? Yeah, so this was 3. And how many constraints did we have? 2 constraints, yeah. Oh yeah, that was the problem. We have 2 equations and 3 unknowns, right? Which we cannot solve. But then if we look at this matrix, that will have the dimensions of 2 by 2. So that's a smaller matrix. And if the rank, if the 2 rows of the constraints are independent, so if we do not write dependent constraints, then you should be able to solve this system. So we can solve this. So we can write mu equals C transpose to the power minus 1 times E. And then we substitute that back into our equation to get our deltas. And we get as a solution, the increments delta are minus C transpose times C transpose to the power of minus 1 times the error we make. And that is the corrections we have to do. And then in a step, we fill that in, we add the correction, and then we calculate again what the constraints are, and then we continue and continue. So this is what we call the least square solution of the problem. And actually in math there is a notation. So if you have this set of equations, we have this set of equations, C times delta is minus E, and we cannot solve that because we have 2 equations and 3 unknowns, then we can solve it. It turns out we can under some assumptions. Under the assumption of a least square solution, we can solve it. And then in math, we usually write that least square solution is C plus times E. Yeah, I should put a minus somewhere because I have a minus here. But the point I want to make is C plus. What is it? Well, actually, it is this matrix. This C transpose times C transpose to the minus 1, and we call that the Moore-Penrose pseudo-inverse. It's a lot of words. Well, if that's an inverse, we agree. That it's pseudo, we also agree because there are probably an infinite number of inverse solutions for the inverse mappings. So therefore pseudo, because it's not a real inverse. And Moore-Penrose, well, that has to do with 2 people, Mr. Moore and Mr. Penrose. And they came up with the idea, 2 mathematicians. And it's even implemented in MATLAB, and in MATLAB it's called PINF, pseudo-inverse. So if you do PINF, you get this matrix. But you can also do it yourself. Okay, now this looks like a lot of math and a lot of magic. So let's make it concrete. Let's do an example. Very simple example. So to see how the system works. And the example is like this. I make it easy for myself that I do a linear problem now. Makes it a bit more easier. So my linear problem is I have equations like C times X is 0. And my C matrix is, what did I choose? -1, 1, 0. And the other one, yeah, 0, -1, 1. So I have 3 x's. Or in other words, the equations I have, I only have 2 equations, 2 linear equations, they're linear. And they read minus x1 plus x2 is 0, and the other one is minus x2 plus x3 is 0. Or in other words, between us, all the x's should be the same. If x1 is x2 and if x2 is x3, then all the x's are x. Okay, so that we know that is the solution which fulfills these constraints. But we also know that there are an infinite number of solutions. Oh, what do I do now? But our approximate solution turns out to be, I shouldn't shift too much, our approximate solution in the process of numerical integration, or somebody in the audience, or I don't know, said, well, our starting point is 0.911. Yeah? Almost right. Almost identical are they. And now we have to find a way to get back on that constraint surface. If we calculate what the constraints are, so if we do C times this delta x, so the error we calculate, then what is the answer? 0.10, I think. Is that correct? Yeah, that's the error. So this is an error. We want to get rid of it. And the error should go to 0. We want all zeros. And the question is, which x fulfills that? Well, you in the audience will probably say, well, I already know the answer, and that is 111. And I say, yes, you're right in the sense that it fulfills the constraints, but is this distance, x minus x, is that really minimal? Or is there a point in the vicinity of these coordinates which is closer and still fulfills the constraint? And if you think deep on it, you think, yeah, probably, because here I just add 0.1, but if I want to spread out all the changes, then it's probably closer. So if I do a little bit addition here and a little bit subtraction there, then the distance between the two solutions will be smaller, and I'm still on the surface. But we don't have to think so hard, we just can solve it, because we know how the least square solution goes, right? So we have our error. So the things we have to calculate for our pseudo-inverse are the C times C transpose. Well, we have our C matrix. So C times C transpose equals minus 1, 1, 0, 0, minus 1, 1, times this matrix, which is minus 1, 1, 0, 0, minus 1, 1. And I'm going to make a whole lot of errors, so you have to help me. Yeah, not in making the errors, but getting rid of the errors. 2, and what do we get here? Minus 1, And I know for sure that we have to get minus 1 here. Why? Yeah, it should be symmetric. And then we get a 2 here. Okay, let me check. Yeah, it's running. Sorry. So we have this matrix. Then what do we have to do? Then we have to take the inverse of the matrix. Yeah. So we have to do the C transpose inverse. Now, why do we do the inverse? Remember that we had this equation C transpose times mu is minus the error, right? So therefore we have to do the inverse, or in other words, the mu, and yeah, mu1, mu2 equals, well, what is the inverse of this matrix? Yeah, it's 2 by 2. And I know a trick. You have to first do the determinant, and then 1 over the determinant. And that is 2 times 2 is 4, minus 1 is 3. 1 over 3, right? And then this entry is this entry. And this entry is minus this entry. No, minus this entry, sorry. Something like this. Now, to be sure, what do we do? Yeah, that's so easy. So we get 4 minus 1 is 3. Yes, that's correct. And then this one times this, that's 0. This one, yeah, that's 0. And yeah, should be the inverse. So we get 1 over 3 and then 2, 1, 1, 2 times this increment, which was the error minus the error was 0.11. 1 over 3, thank you. Super. So that is a super simple answer. Mu1, mu2 equals 0.1 over 3 times, well, the first column, right? 2, 1. And then now I want to know the increments. Yeah. So the increments are the delta x1, the delta x2, and the delta x3 are, and if I remember well, was it not minus C transpose times the mu's? Minus C transpose times these mu's. Or in other words, minus, and then C transpose is this guy. Minus 1, 1, 0. 0, minus 1, 1. Yeah, that's a 1. And then times 0.0 divided by 3. And then 2, 1. Gives us, well, let's keep the 0.0 divided by 3. And then we get, so that's a minus 2. And then here I get a minus 1. Oh no, that's a 1 and a 1. Yeah. So those are the increments. Yeah. Meaning that the new coordinates, so the new coordinates x1, x2, x3 are these values 0.911 plus, yeah, then we get 0.1 times 2/3 with a minus sign, right? And 1/3, 1/3. Oh, I forgot this minus sign. Minus, and then this becomes een gummetje. So this I forgot this minus sign is here, and then it's here. So what do we get? 2 over 3 is 0.66666. But we have to do 1/10 of that, so it's 0.066666. Yeah? So we get 0.9 and a lot of 6's. And then 1 over 3 is 0.3333. And then 1/10 of that, so we shift 1 comma. And so we get, oh yeah, 0.96666, 0.9666, etc. Ah, they're all identical. That is good, because I expected that solution. And now the big question, is it a shorter distance than the 111? Yeah, that's clear, right? You just have to calculate that, but if you remember the, what was it, question number 5 from the quiz, if you take the norm of this one, that's less than 1, so the norm of the whole thing is less than 0.1. And with the other one, we just added 0.1. So it's a shorter solution. And it's really the shortest. It's a unique solution. That's also the beauty. By saying, I want the shortest distance, you find a unique solution. And yes, it's unique and the shortest. Okay, now how do we apply? Yeah, question.
You say the constraint surface is curved.
Yeah, in this case, it's a very simple. It's a plane, yeah. So if you have to envision that, then I'm going to draw with my hands in space because I cannot do 3D drawing. You have a plane and you have a point, and then you say, how can I get back on that plane? And there are, of course, an infinite number of ways, and we know that, of course, the perpendicular distance is the shortest distance. Yeah, then it can be somewhere. Yeah, all nonlinear problems have nonlinear problems can have multiple solutions. Yeah, yeah, totally true. So it's an incremental way, and you're doing a step-by-step approach from one point to the other. We cannot solve the big problem. We can only solve it in the vicinity, in a local area. Yeah. Okay. So then the Gauss-Newton process for us, Gauss-Newton, how does it work? Works for us, for our problem, for our coordinate projection problem when we have the Q's and the constraints and so on. And I'm just gonna write down the algorithm. So it goes like this. First, you set the number of iterations. You set that to 0 because you want to keep track that you're not in an infinite loop. Yeah, because then, if you cannot find a solution, if there's no convergence, then the computer starts running and you have to press Control-Alt-Delete. Famous reset. The next thing you have to define is, when do I stop my algorithm? When am I happy? What is my tolerance? So for now we can say, well, with the machine accuracy we know, we set our tolerance to 10 to the minus 12 as a relative error. That's okay. And then we start by setting the value Qn plus 1 equal to the approximate value. Yeah? And these are, of course, all vectors. So we start by saying, well, our solution is the approximate solution. And then let's also set our max number of iterations. Well, it's a second order process. It's a Gauss-Newton process. So it should converge quadratically. So, well, 10 iterations should be really the max. If you're then not converged, then there's something rotten in the state of Denmark. Yeah? Okay. And then what do? Well, first let's evaluate what the constraints are. So we evaluate our error in the constraints and by just putting in the number. And then, of course, you will see that's not 0, but I'm going to make a repeat loop out of it. So I say repeat, and then until some criteria. Now what I'm going to do is I'm going to calculate that increment, delta Qn plus 1. And how am I going to do that? Well, I can write C plus, but for now let's say we do minus C comma Q transpose times C comma Q, C comma, this is Jacobian, minus 1 times this error. So that is our increment we do. Then we update our coordinates. So we had our coordinates, and we're going to update it with this increment. And of course, now we have to evaluate what the constraint values are. Don't zoom. So we're going to evaluate. We say, well, let's calculate the error again. C of the Qn plus 1. And then we increment our number of iterations, because we've done an iterations. Iterations is iterations plus 1. And then now we get our until clause. And our until clause is, when do we have to stop? Well, we have to stop when we have reached the maximum number of iterations. So if iterat is larger than max iterat, we stop. So that is one. Or it's an or clause, it's not an end clause. Or if the error is less than the error in the constraints is less than our tolerance, so you could say the max of the absolute value of this error is less than this tolerance. And if you do this process, then you will see that in 2 or 3 steps, and bang, 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 you're back on the surface. Because already the numerical integration result is pretty accurate. It's already a very accurate result. And actually, we call this, by the way, this whole process is called coordinate projection method. And some mathematicians, Ada Eichzollner and Klaus Führer, have written a small book on multibody dynamics, but they're actually mathematicians, and they prove that if you add this coordinate projection to a numerical integration step, that the error you make some error here, because you are in a point which the numerical integration scheme predicts, and then you're going to change that point a little bit. And maybe your whole numerical error, your numerical method then breaks down, because your whole error estimate breaks down because you're changing the numbers. Well, they prove that the change you make is within the order of the truncation error of the numerical integration method. It's all within that same h to the power p. So coordinate projection will always work. And that is very nice to know. We have a little bit more time, and I wanted to talk actually about a very old book. And I'm really sorry that I didn't take the book with me, because it is in one of my boxes and I don't know which box. I had to move from one room to the other. But first let me picture. I want to talk about a book, and that is the famous the famous book Analysis of 4-bar linkages. And you don't see it like this on the screen, but let me picture. It's a folio format book. So folio means this height, this width, and the thickness. The folio doesn't tell you about the thickness, but it's this thick. So many pages. Large book with many pages. And the cover is green. Oh, that doesn't really matter. Analysis of 4-bar linkages. So you would think, why do you write a folio book this size, this thickness, on one 4-bar linkage? Well, let's go back in time. We are in 1950, and we work for the shoe company, right? And we have to come up with mechanisms for our machines to make shoes and to stitch them and make soles and whatever. I don't know how they work. To design those mechanisms, you need a synthesis process. So not an analysis, but synthesis. And synthesis, you could say, to synthesize a motion, you could do repeated analysis and then change parameters and then see, is it the motion I want? Well, actually, the book they made is a book to synthesize a mechanism. And how do you do that? By flipping the pages. And which pages? Well, let's go quickly to the pages. These are the pages on the book. So, page after page after page, you see a mechanism. And is it a 4-bar mechanism? Yeah, it is a 4-bar. Because 1 bar, 2 bar, 3 bar, and this is the support. And this is the input motion, the circle, and we are interested in the output motion of a point. And this point is a member of this bar, the middle bar. And we call that a coupler curve. So when it does one revolution, and you take this point initially on this bar, then this point will follow this curve. And so they made for this whole plane, which is connected to this bar, they made here this whole array of points, and they show this whole array of curves. There's an interesting one here. Ooh. Or here there's almost a flat part. Those things we are usually seeking, straight parts, where we have a rotary motion and we want to have a straight motion. Anyway, the book goes on and on and on and on, page after page after page. And oh yeah, on the right you see the layout of the mechanism with the dimensions of the bars and of course the grid points for this coupler curve. And so you just flip through the book to find the motion you want. You can even think of a desired speed profile you want, because what they did, you see these dashed lines, and the dashes are not random. The dashes are such that they are equally divided among this circle. meaning that looking at this curve, you can see, oh, here it's going zzz, and here it's going very slow, 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 and then it's speeding up zzz, and then, so you can have an idea of speed. Moreover, you can even calculate that, because you know how many dashes there are here, and given those numbers, you can just calculate from the dashes here and the length, you just take a ruler, what the speed is there. So this transfer function, this transmission function, input speed, output speed, it's there. There's also a unique way to calculate the accelerations even, given you have these dashes. That's also possible. And how do you do that? Well, then we have to go to page 1, and we have to read a little bit of the introduction. So we now know what the book is about. And then it talks about 4-bar linkage. It shows the mechanism. By the way, how did they generate these graphs?
I was thinking by hand.
Almost right. With a mechanism, yeah, Lisa, very good. A mechanism. So they just built the thing, and they generated the graphs. Of course, you can do the analysis. I mean, you can go through the math, and here they mention the math. So people who want to do the math, that's okay, they say, if you want to do that. But we generated this atlas just with the machine. It's nice that you make an atlas where you design curves with a machine as purpose to design a machine, right? That's sort of cool, I think. Anyway, and then it explains a little bit about the dashes and the motions and so on. Here you see, and it gives a number of examples. So here you see a nice mechanism. So this is the coupler point on this bar, and you see a nice straight segment. And notice also the dashes that the speed is also pretty constant here. Yeah. And then it gives a number of examples to understand how this all works. This is with the equal steps here and the unequal steps here. Anyway, why do I show this? Because this was 1950 and we are now in 2018. And as a homework problem on the fly in 1 week, you just do this. And even more than that. I mean, with your MATLAB program, you just can calculate all those curves. And with a little bit of extra, you can even just do the synthesis, the design of such a mechanism by using some fmin-con or something like that within MATLAB. That is my take-home message. We have 3 weeks, a break of 3 weeks. After 3 weeks, we continue, May 24. See you then.